Thanks for this nice introduction, and let me also thank Edgar and Damian for this invitation. I'm overjoyed to participate in this session. Here. And I'm going to talk about a joint work with the first speaker of this session, Ederson Moreira dos Santos from ICMC and Nicola Suave from Milan. First of all, let me say what I understand by a unique continuation principle. To fix the ideas, let us consider a solution U of some scalar PD. Then I'm gonna ask whether or not the solution vanishes in the whole domain. And the usual types of UCP that we are going to consider are three. The first one is when the solution vanishes with some, let me say, has a strong vanishing at some point. So the solution at U0, at this point here, is equals to 0. So the second situation is when the solution vanishes in an open set contained in the domain. And the third one is when both the solution and its derivative, let me say the normal derivative, vanish on a portion of the boundary. Okay, and the conclusion is always the same. I'm gonna state that the solution vanishes in the whole domain. And in this talk, we are going to focus on solutions of the system, as some special system like f of u and v equals to 0, solution of some g here, u v equals to 0, and the question is the same. I'm gonna ask when both u and v vanish in the whole domain, provided that we have some suitable vanishings that I'm going to specify in the talk. Okay, just to give you an example, in the scalar case that we are going to use, when this f here is equals to u to the power p in modulus, then these three types of UCP, they hold true. So let us observe now what happens with solutions of the system. The model case that I have in mind is the following Lane-Emden system, which is quite famous because of 30 years conjecture, which says that in the plane PQ, composed by these exponents here, P and Q, it says the conjecture that we don't have solutions between two hyperbolas on the plane. The first one is the PQ equals to 1, which corresponds to the linear case P equals to 1 in the scalar case. And the second one is this hyperbola here, which is the conjecture critical hyperbola. And the conjecture says that we don't have solutions between these two hyperbolas. So this H hyperbola here, it should play the role of the critical exponent in the scalar case, which is equals to n plus 2 n over n minus 2. Because when we are on or above the hyperbola, let us say here, then we do have positive solutions of this system. So as a dual problem, we expect not having solutions, since we have solutions in Rn, we expect not having solutions in a bounded domain. And this is our motivation for unique continuation. Again, I'm considering here this region here, which corresponds to this case here, which is the supercritical or critical, in which we are on or above this hyperbola H. And in this case, we are going to ask if there is or not a solution or a non-trivial solution of this system in a bounded domain when subject to Dirichlet boundary condition, here equals to 0. And the usual way of looking at this problem is by using a Overdrive identity like this, which holds for the solutions of the system whenever we have some star-shaped domain. So here I am considering the ball. And whenever we are in this region here, in the supercritical or critical, then this part here, in brackets, it has a sign. And so the right-hand side of this equation is non-positive. And in order to reach a contradiction from the existence of a non-trivial solution for this system, it would be enough to have some sign on this function here, inside the integral sign, and prove, for instance, that this is positive on the boundary. So, when we have a positive or negative solution, which means that both components U and V are both positive or negative, then this sign here is just a consequence of the Hopf lemma. So this is okay. So what happens when we have solutions not necessarily signed? And let us start with the scalar case. So let me consider the case when P is equals to Q and U is equals to V. So in this case, we automatically see that this has a sign here because it appears the derivative square, right? So when we are in the supercritical case, when P is larger than P star, this quantity here is negative. So the left-hand side is negative because we are dealing with a non-trivial solution. So in this case, it is done just because of the sign. But when we are exactly at the critical exponent, a magic happens here because then we have this identically 0, which means that such solution, which is a solution of the Dirichlet problem, so this solution together with its derivative, they both vanish on the boundary because of this identically 0 sign here. So a UCP here, a unique continuation result of type 3 that we have seen, this UCP applies in order to obtain that the solution is trivial. So this is where a unique continuation result enters to show non-existence of solutions in the supercritical or critical regimes. So what about the system? In scalar case is okay. In the case of the system, our contribution was to show that not necessarily signed solutions of the system do not exist in the supercritical or critical regimes, but only in the radial case. And this is our result. Actually, it applies for solutions, even for solutions of more general equations obtained with operators of fully nonlinear type, even for non-differentiable ones. And we have this boundary UCP, which is quite strong because here we are supposing that both components are vanishing on the boundary, but only one of the derivatives is vanishing on the boundary. So in this case, we obtain this result. And actually, this comes from a more general alternative result from which this theorem is just a corollary, but this more general result says that in fact we have these two situations. Either these are which is a 0 for both of them here. Either this, in the situation number 1, either it's 0 is isolated for both of them, and in this case we already obtained that the product of the derivatives is positive, from which we derive the non-existence result as we have seen. And so we are left to show that only in the second situation that we don't have a isolated 0 is when the solution is trivial. Let us say, for instance, that it's U that has, let me just comment the first one first. First things first. And in the first case, when the solutions, when these R is as an isolated 0 for both of them, it means that both of them has a well-defined sign near the boundary. So we can see by the maximum principle that if they have a sign, they need to have the same sign. And so by Hopf lemma, we conclude this situation. So let us show now that the second case, when we have one of them having a non-isolated 0, then the solution must be trivial. And mean that we have a non-isolated 0, recall that we are talking about radial solutions, so the nodal sets are just spheres. So if we have a non-isolated 0, it means that we have a sequence of spheres converging to the boundaries such that one of them, let us say U, vanish in each of these spheres. Okay, and for instance, we can take some small annuli like this, or we can choose this epsilon small, such that U is equals to 0 on this boundary of this annuli. And so up to replacing the pair UV by minus U minus V, we can assume that V at R minus epsilon is less or equal than 0. Recall that at the boundary V, it vanishes on the boundary, so we just need to control the R minus epsilon 1. And so with this, both of them have well-defined signs on the boundary of this annuli, and then we may apply the ABP inequality for each of these scalar equations here. And so, since here it appears some power, we can take this power to the first equation and combine the two inequalities in order to obtain such estimate. And then we see that if this epsilon is chosen such that small is enough, such that this is less or equal than 1/2, then this V is less or equal than 0 in this whole annuli. And with this, we see that U also, since this supremum here is going to be 0, then this is also, then the supremum of U is also less or equal than 0, and then by the strong maximum principle, it needs to vanish on this whole annuli, the solution U, and so we can see the same for V, and with this we conclude that both of them vanish in this annuli. And so we just need, since this epsilon can be made uniform for a fixed solution, this does not depend on this, we can make this epsilon uniform. So this, with this we propagate this vanishing to the whole BR ball. And this is more or less the idea of the proof. Let me just comment that this was possible because here it appears the superlinearity condition in such a way that whenever PQ is larger or equal than 1, then this can make uniform because this is just a constant. But The situation is a bit more delicate when we are in the sublinear case, like this one. So we can construct a simple example by showing that dead coarse solutions may appear in this case. And here I I'm presenting just one in the case of one-dimensional and with the Laplacian operator, but I recommend this beautiful work of Damião and Rafael for more general fully nonlinear operators with the minus sign here. Okay. And so what happens now when we are talking about UCP, unique continuation for non-radial solutions? In this case, we're going to be able to prove such a strong unique continuation, the type 1 that we have seen, in terms of a vanishing, that what I will mean by a vanishing is a strong vanishing in the sense of vanishing with infinite order in this sense. And as soon as we have both of the components U and V vanishing at the same point with infinite ordering, then we obtain that this solution must be trivial. And just to give you an idea of the proof, actually in this case, let me just say that in this case we are going to consider just the Laplacian operator, because in fact our arguments will rely on some free boundary techniques, in special this Caffarelli-Friedman lemma, this fundamental lemma, which furnishes the asymptotic behavior of solutions near its of a solution near its nodal set. Okay, so with this at hand and having a solution of the system, we use the Lipschitz condition, Lipschitz assumption that we are making on the solution, in order to measure as a power of x estimate the Laplace of u in some bulb. Let us consider, for instance, that the point x0 is 0, and since we are going to make a local argument in order to show that both solutions, we are going to more or less do the same thing by showing that the solution must vanish. This solution pair must vanish in a smaller ball. We can consider that we are in a ball B1, for instance. And with this estimate, we apply the Caffarelli-Friedman lemma and decompose U as a sum of a polynomial, of a harmonical polynomial, and some function with prescribed asymptotics. And since U vanishes with infinite order at the point 0, this harmonic polynomial must be 0. And so actually this function U must coincide with this gamma 1. And since we have these asymptotics for the U, we may in the next step by using the coupling, estimate the Laplace of V, and again we use the Caffarelli-Friedman lemma to decompose V as a sum, and since V also vanishes with infinite order at the point 0, V also coincides with the function that we have the estimate, and so on. We iterate this result, and after some detailed analysis on the constants and on these exponents, alpha k and beta k, that I won't bother you with the technical details, but essentially the things that these two are comparable with pq to the power k. And so after some calculations, we show that U has this estimate, and in the ball B1. And here is again the magic, because by taking this ball small enough, then we're able to control this constant k by a power of x, and with that we make it appears here this superlinearity condition again. This is positive because PQ now is larger than 1 strictly. And since we are in the ball B1, this here is negative, so the expression in brackets converts to minus infinite when k goes to infinite. And so we obtain that this solution must vanish in this smaller ball BR bar, where this is the constant here. Okay, and so since we have this vanishing on this ball, and we apply this on the other equation, and we use a strong unique continuation for the equation, plus regularity of solution of harmonic functions, to obtain that V also vanishes in this ball as well. So after that, since we can take this to be, again, uniform depending only on the fixed solution, then we can propagate again this vanishing to the whole domain. And this is more or less the idea. I don't know if I have time, but just if I don't have time, you can say me. But just to finish, let me just comment some two consequences of this strong UCP for the system. The first one is a weak UCP, which says that if we have either U or V, this is a little bit stronger because we are supposing that only one of them vanishes in an open set. Let us say U, in an open set of this domain omega. If U vanishes in this open set, then since we are considering a strongly coupled system, it means that V also vanishes in this open set. And so since both of them vanish in this whole open set, then in particular they vanish with infinite ordering at a point. Let us say at a point x0 belonging to this set. And so we apply the strong UCP by concluding that both of them vanish in the domain. The second consequence is a boundary unique continuation. And in here, I need to suppose that both U and V vanish together with their two derivatives in a portion of the boundary. Let us say something like this, in a portion here. And so if everyone vanishes in this portion of the boundary, it means that, and we have a solution which is C1 at that portion, it means that I can make an extension here of this solution and of the coefficients of the equation also. And at this part above the domain, I can define them to be 0, for instance, because they all vanish in this portion. So here in particular is an open set such that the solution, both components here vanish in this open set. And so we apply the weak UCP by concluding that they need to vanish in the whole domain. Okay? And just to finish, let me highlight that it's still an open and challenging question to show that to see whether or not we have solutions or not in the supercritical or critical regimes, and if this has a relation with unique continuation principles. Thanks.